This is a few slides to analyze the limiting reactant investigation that is done by recording pressures. We're going to convert your graphical data from LoggerPro into a chart that can help you draw logical conclusions about the stoichiometry of a chemical reaction. Here's what you did. You placed 50 milliliters of sodium hydrogen carbonate solution into an Erlenmeyer flask, and you did this 7 times. In the first run, you added no acetic acid, so there would be no reaction. And you swirled the mixture for 90 seconds as you recorded the total pressure in the flask. It didn't go up much. This control run would show what pressure increase or decrease would occur if there were no chemical reaction, because there were no chemical reactions going on in that flask. You recorded the maximum pressure in this control run. Then for each successive run, you added 1 milliliter of acetic acid more than the previous run, until in the last run you added 7 milliliters of the acid and recorded the pressure. The graphs you produced on one set of coordinate axes are on a later slide. Let's talk about the calculations. So the first is, how many millimoles of sodium hydrogen carbonate could react in each run? You had the same 50 milliliters of the solution in each run, and they were all the same concentration. So the molarity, we made it as 0.030 molar, and that's 0.030 millimoles in every milliliter. You used 50 milliliters of this solution. When we multiply that by 0.030 millimoles per milliliter, you get 1.5 millimoles of this weak base sodium hydrogen carbonate in your flask. You then added acetic acid. Here's the acid calculations. We call acetic acid HOAC for short. The acetic acid in dilute vinegar is 2.5% by mass. It just comes right from the grocery store at 5%, and we dilute it 50%. So it's 2.5% by mass. So how many grams would there be in 100 milliliters of vinegar when you consider that 1 milliliter is 1 gram? Well, 2.5 grams then. How many grams are in each milliliter of the vinegar? Either 0.025 grams or 25 milligrams. That means the millimoles of acetic acid in each milliliter would be 25 milligrams times 1 millimole over 60 milligrams, the molar mass of CH3COOH. When you multiply those together, you get 0.417 millimoles in each milliliter of the sodium hydrogen carbonate. We can then go for, in this case, we have 8 lines because we used the 0 as volume, and found the number of millimoles of acetic acid in each run. And we check our calculations and we see that it goes from 0 in the first run, where there's no acetic acid, to 2.92 millimoles in the last run, or 7 milliliters. This is a graph that you would get if you tracked time versus pressure in kPa. And you'll see that this is magnified because it's got a 97 kPa at the bottom and about 104 at the top. The maximum pressure at 90 seconds is shown, but the control pressure, which is down here at the bottom, must be subtracted if you're going to get a good increase in the carbon dioxide pressure that's due only to the addition of the gas from the reaction. This is the control pressure at 90 seconds down here at the bottom. You see it's 98.06. You then find the 90-second pressure for each of the other 7 runs, subtract this 98.06 control pressure, and you graph that against the concentration of each acetic acid sample. So we're actually, since we have constant volume and constant temperature, we're actually getting a good measure of the number of moles of carbon dioxide gas that's produced. Here's a graph of that added pressure from the carbon dioxide versus the millimoles of acetic acid that were added to it. Where is the equivalence point? That is, where would the acetic acid millimoles and the sodium hydrogen carbonate millimoles be exactly the same? Well, if you think about it, this graph shows that an increasing amount of acetic acid gave you an increasing amount of carbon dioxide until this point, and then adding more acetic acid did next to nothing to the pressure over and above what was happening here. And that we call the equivalence point. The acetic acid is completely used up by 1.6 millimoles. That's very close to the 1.5 millimoles of sodium hydrogen carbonate that we originally put into the flask. This confirms the 1.0 ratio of millimoles of acetic acid to sodium hydrogen carbonate that is shown in the equation. And this is the equation that we use for this particular reaction. You will notice that the hydrogen ion from the acetic acid and the OH from the hydrogen carbonate join to form water. That proves that this is an acid-base reaction. You will also see that the rest of the hydrogen carbonate ion has come off as the hydrogen carbonate was split up. It's come off as carbon dioxide gas. And finally, the acetate ion really hadn't done anything. It just keeps floating around in the water. And you might remember what the name of ions that do not participate in the reaction would be, and put that into your notes.